Today we're going to prove Fermat's little theorem using mathematical induction. Now we're going to use effect regarding the binomial coefficient. Recall that n choose k, the formula here is going to be a fraction here, n factorial over k factorial times n minus k factorial. Usually you would cancel certain terms and you live with k terms on the top and on the bottom. Now when n is a prime number p, we claim that the coefficient here, p choose k, is a multiple of p. Of course, k here is going to be less than p greater than 0. Because when k equal to 0 or equal to p, then the coefficient here is going to be 1. For anything else in the middle, that's multiple of p for the prime number. For example, 7 choose 3 is going to be multiple of 7. Now here, how do we prove that? Now we use a formula here. Notice that you can replace the fraction here by canceling certain terms, live with k terms on the top and on the bottom, and you take p by itself. Notice that p is a prime number, so you do not have any common factor in the denominator here, 1 through k, because k is less than p here, right? We assume. Now you reduce the fraction to s over t. You make the argument that t cannot have any common factor with p. So since we know p choose k, the whole thing is an integer, so s over t must be an integer. Let's assume it's a z. So that is a multiple of p. So we have proven, due to the fact that p is a prime number, so p has to divide p choose k, where k is greater than 0, less than p. Okay, we're going to use that in the proof. So what is the Fermat little theorem? Now we claim that a for integer raised to p's power is congruent to a mod p when p is a prime number, p is a positive prime number. All right. So in some other textbook, you may see a different form. That is, we say that when p does not divide a, so a is some number that is co-prime to p, then we say that a raised to p minus 1's power congruent to 1 mod p. That's a different version of the theorem. We're going to stick with the first version. Okay, so how do we prove that? We're going to use mathematical induction on the integer a. So we say a is integer. Now we can assume a is always non-negative, because if a is negative, you can always use congruent key modulus arithmetics to turn that into non-negative. With that, the base case would be a equals 0. Yeah, when a equals 0, p is a positive number, is a positive prime number. So we know that 0 to the p equal to 0. The condition, of course, obviously it holds, right? So the base case, that's true. Now for the induction step, we assume for a fixed non-negative integer a, we assume a raised to the p's power is congruent to a mod p. Now we can argue a plus 1. Now a plus 1 raised to the p's power, we use binomial expansion here. Notice that earlier we know that p choose k for the intermediate term is a multiple of p. So in modular arithmetics, those terms can be cancelled, right? So only live with the first and the last term, which is when k equals 0 and k equals p. So what we have is congruent to a raised to p's power plus 1 raised to p's power. Of course, 1 raised to p's power, that's 1. A raised to p's power by the induction hypothesis, it is congruent to a. So this whole thing here congruent to a plus 1. That is, we have concluded that is a plus 1 raised to p's power is congruent to a plus 1. This is exactly the induction step, right? So by mathematical induction A, we have proven that the statement is true for all non-negative integer a. So that is, we have proven the Fermat little theorem in this format. Now earlier we mentioned there is alternative version where the a is more restrictive here, saying that p does not divide a, integer a, that is a and p are co-prime. So what you can do from our version that we have just proven, you can just use the fact that when they are co-prime, there is this multiplicative inverse of A, right? You multiply that on both sides, you're going to have this version here. Okay, so we can leave that as an exercise to prove this version of the theorem. Hope you enjoyed the video. Please like, share, and subscribe to the channel.